It was 1964. The Cold War was heating up, and every second counted in the sky. Conventional reconnaissance planes were too slow, too vulnerable. Then Lockheed unveiled the SR-71 Blackbird, a plane that could fly faster than 2,200 miles per hour and higher than almost any missile could reach. On paper, it shouldn't have worked. Yet, time and again, it outran every threat. How? And why could no missile ever catch it? The Cold War was a game of intelligence. Every minute counts when you need photos of enemy installations. Conventional reconnaissance aircraft were too slow, too vulnerable. Enter the SR-71, cruising at Mach 3.2, over 3 times the speed of sound, and at altitudes above 85,000 feet. But hitting a target isn't just about pointing and shooting. A missile has limits: maximum speed, acceleration, and guidance. To catch a plane like the SR-71, it has to overcome extreme aerodynamic and physical barriers. Relative speed: at Mach 3.2, the SR-71 is covering roughly 2,200 miles per hour. Many surface-to-air missiles at the time maxed out around Mach 2.5. That's a fundamental problem: the missile is inherently slower. Drag and atmospheric density: the higher you fly, the thinner the air. Drag decreases, which is good for the plane, but also reduces the effectiveness of the missile's aerodynamic control surfaces. Missiles rely on air to maneuver. At 85,000 feet, even small course corrections become sluggish. Thermal stress: at Mach 3+, the SR-71's skin heats up to over 500 degrees Celsius due to air friction. That's why engineers use titanium alloys, which maintain structural integrity under extreme temperatures, something missiles aren't built to withstand mid-flight for long durations. Narrator: skeptical. Some marketing claims suggest modern missiles could outrun anything. But physics doesn't lie. Acceleration, drag, and maneuverability set a hard ceiling. So how did Lockheed engineers make this plane untouchable? Shape and aerodynamics: the Blackbird has a long, slender fuselage and chins along the nose and wings. These aren't just for stealth, they reduce drag and delay shockwave formation, allowing sustained supersonic cruise. Engine ingenuity: its Pratt & Whitney J58 engines were a hybrid between a turbojet and a ramjet. At high speeds, much of the thrust comes from air compressed by the plane itself, essentially turning the plane into its own jet engine. Flight tactics: the SR-71 didn't just rely on speed, it climbed, accelerated, and performed evasive maneuvers at altitudes where missiles were sluggish and radar guidance struggled. It's a classic case of first principles engineering: the laws of motion, thermodynamics, and aerodynamics dictated the design. There was no shortcut. Of course, nothing comes free. Fuel consumption: Mach 3 flight burns thousands of gallons per hour. The SR-71 needed in-flight refueling for almost every mission. Material cost: titanium isn't cheap, and machining it to tolerances required new fabrication techniques. Maintenance: flying hotter than metal usually meant constant inspections and replacement of parts. The Blackbird solved one problem at the cost of enormous operational complexity. But for intelligence at that level, it was worth it. Let's put it in perspective. To intercept an SR-71, a missile would need to accelerate faster than Mach 3.2 and maneuver at altitudes above 80,000 feet. That's enough energy to power a small city for a day, per missile launch. Even today, few systems can reliably hit such a target, and modern stealth and electronic countermeasures make it even harder. The State Route 71 isn't just a plane, it's a lesson in engineering compromise, speed, altitude, and stealth at the cost of cost and complexity. Missiles couldn't catch it because physics demanded they solve an impossible problem. Economic reality, building something faster than 3,000 kilometers per hour isn't cheap. And the maintenance alone could bankrupt a small air force. Human ingenuity versus nature. Sometimes, the limits aren't in our imagination, but in the air itself. Yet, by thinking from first principles, engineers bent the rules just enough to make the impossible routine. The Blackbird reminds us, the sky doesn't just reward speed, it rewards understanding. And when you respect physics, even missiles can't keep up. Asterisk, as the State Route 71 cruises above the stratosphere, Mach 3 airflow ripples along its fuselage, and the heat shimmer of supersonic friction glows along its nose and wings. From this height, the sky itself becomes a shield, missiles struggle, their guidance faltering in the thin air. Every line, every chine, every curve of the Blackbird was dictated by first principles. Speed alone wouldn't suffice. Engineers bent the laws of aerodynamics, thermodynamics, and physics just enough to make the impossible routine. The energy required to intercept this plane? Staggering. Enough to power a small city for a day, per missile launch. And even today, few systems can reliably track a target this fast, this high, with stealth and electronic countermeasures in play. Flying faster than 3,000 kilometers per hour comes at a cost: titanium alloys, constant maintenance, and enormous fuel consumption. Yet human ingenuity turned these challenges into advantages. The State Route 71 is more than a plane. It is a lesson in respecting the limits of nature, a testament to engineering compromise, and a reminder that when physics is understood, even missiles can't keep up. The sky rewards those who think from first principles. And the Blackbird was, and still is, untouchable. Asterisk. Notes for pacing/styling. 280 words fits roughly 2 minutes. Pauses after phrases like, missiles struggle, the impossible routine, and, even missiles can't keep up, create cinematic emphasis. Perfect for syncing with Batch 8 AI visuals, stratosphere shots, airflow lines, thermal glow, HUD overlays, energy comparisons.